So last time we had started talking about the reactions of the alcohols, and we talked about acid-base reactions, and we also talked about the E1 dehydration of an alcohol to form an alkene. So let's just recap that briefly. Recap of last time said that we have an alcohol and the carbon that bears the OH group of the alcohol, that is called the alpha carbon. The carbon next door to the alpha carbon is the beta carbon, and the beta carbon has a proton on it, and this carbon has to be sp3 hybridized, as does this one, right? So it's not just any alcohol next to any other carbon atom. So it has to have these hybridization states. And we talked about how when the alcohol reacts with acid and heat, that little triangle, that's a symbol for heat, this results in the dehydration of the alcohol, in which there's now a new double bond between what used to be the alpha carbon and the beta carbon. And the other product of this reaction is water. This is a dehydration of an alcohol. Okay, and we talked about the mechanism of the reaction. The first step in the mechanism would be the protonation of the alcohol to form an oxonium ion. And then the oxonium ion leaves. The oxonium ion departs, and upon its departure, you get a carbocation, right? This is the carbocation. And then a base in the solution comes along and removes the beta proton from the beta carbon. And that is how we get that alkene between alpha and beta. So notice the reaction is catalyzed by acid. Acid gets the proton, gets the reaction mechanism started, but the last step of the reaction mechanism is going to be the disgorging of a proton into the reaction mixture. So the proton takes part in the reaction mixture, in the reaction mechanism, but it's not consumed stoichiometrically. So it's catalyzed by acid. Okay, so that was kind of very entry-level stuff. And then we talked about one of the complications of acid catalyzed dehydration of an alcohol, and also it's a complication that attends any kind of mechanism that involves a carbocation, which is the possibility for the rearrangement of the carbocation. And we talked about how the most stable carbocations are resonance stabilized, and then tertiary, then secondary, then primary, then superprimary or methyl. Those are the least stable. And we talked about how a carbocation rearrangement happens when we can go from a less stable ion to a more stable ion. Okay, and we were talking about this reaction. And what I'd like to do now that I finished recapping last time, what I'd like to do now is write out the mechanism for this reaction. And in the mechanism of the reaction, we are using these curved arrows to show the motion of electrons, right? Okay, so let's write out a mechanism for this reaction. Well, first step is going to be what? Protonation of the alcohol oxygen to form an oxonium ion. So this is a theme that we see repeatedly. So this oxygen has some unshared electrons on it, and the oxygen atom uses those protons to uses those electrons to snag a proton from the solution. And so we get the oxonium ion, which has that positive charge on oxygen. And then the oxonium ion departs as a molecule of water. And so we get this carbocation. Okay, so now this carbocation is secondary, but it is secondary and attached to a 5-membered ring. And maybe you know from Orgo 1 that 5-membered rings are not as good as 6-membered rings, because 5-membered rings have strain, whereas 6-membered rings have less strain. So what this carbocation is going to do is it's going to undergo a rearrangement. And we know that just by looking at the product here. We have to find a way to blow this 5-membered ring up into a 6-membered ring. And how is that going to happen? By a carbocation rearrangement. So let's remember how a carbocation rearrangement works. Is that we call the carbon that has the positive charge, we call that carbon 1. Neighboring carbon is carbon 2. So this guy has two neighboring carbons. It has 2 carbon 2s. Okay, and now something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1. The charge is going to move from carbon 1 to carbon 2. And we always have to remember that the carbocation rearrangement is going to feature going from a less stable ion to a more stable ion. So we always have to remember our order of carbocation stabilities. Okay, so I want to return to this structure, but let's table him for a moment, right? What I want to do is I want to copy that structure down again, maybe for those of you who are less familiar with carbocation rearrangements. So I want to want to talk about what this thing is going to do in detail. We're going to come back to this mechanism in a second, but let's talk about what this, how to analyze a carbocation rearrangement in case you've never seen something like this before. Okay, so there's carbon 1, there's carbon 2. Something bonded to carbon 2 is going to pull out of carbon 1. And it's something bonded to carbon 2 is going to pull out of carbon 2. It's going to plug into carbon 1, and the charge is going to move from carbon 1 to carbon 2. So what all is bonded to carbon 2? Well, there's a hydrogen there, right? He's bonded to carbon 2. He could pull out of carbon 2. He could plug into carbon 1. And the charge will move from carbon 1 to carbon 2. Okay, so that's a possible rearrangement. But that's not the rearrangement that happens in our case, because we have to figure out a way to blow this 5-membered ring up into a 6-membered ring, right? And this just doesn't cut it. It's still a 5-membered ring. So although that is a possible carbocation rearrangement, that is not the rearrangement that's involved in the mechanism we're talking about. Okay, so let's look at another possibility. All right, there's that. carbon 1, there's carbon 2. Another thing that's bonded to carbon 2 is this methyl group. He could pull out of carbon 2. He could plug into carbon 1. But this has all kinds of problems with it because it not only does that not give us a 6-membered ring, it also makes it's also a degenerate carbocation rearrangement. We're going from a secondary to a secondary. So that is not, that's not in the cards here either. Okay, so this is how we figure out what migrates. It's a trial and error procedure. You're looking at carbon 1, you're looking at carbon 2. Something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1, and the charge is going to move from 1 to 2. So there's our carbon 1, there's our carbon 2. What else is bonded to carbon 2 is this hydrogen. He could pull out of carbon 2. He could plug into carbon 1. And the charge could move from carbon 1 to carbon 2. So that's another possible rearrangement. But once again, no good, because this doesn't blow, none of these rearrangements blow that 5-membered ring up into a 6-membered ring, which we need. So all of these, no good. But this is how we determine what migrates. It's a trial and error procedure. What is going to go from a less stable ion to a more stable ion and is going to advance us toward our product? Okay, so we treated that in some detail. So now let's return to our reaction mechanism and see what exactly does migrate and what exactly does happen. Okay, so this guy right here, this carbon atom right here, I'm going to put a dot on him. He's bonded to carbon 2. He pulls out of carbon 2. He plugs into carbon 1, and the charge moves from 1 to 2. So we can symbolize that with this motion of arrows like that. And I'm going to try to draw this. So there's the dot. He used to be bonded to carbon 2, but is no longer bonded to carbon 2. Now he's bonded to carbon 1. There's carbon 2 right there. There's carbon 1 up here, and carbon 1 has this fishtail on him, and the charge moved from 1 to 2. So he's there now. Okay, and so now this is what's happening, because we've blown that 5-membered ring up into a 1, 2, 3, 4, 5, 6, and back again. We've blown this guy up into a 6-membered ring. This is kind of an ugly drawing, so let's fix it. It's a 6-membered ring with a fishtail like that, and the positive charge is over here. And you see, we've gone from a strained secondary ion, that was secondary and had that 5-membered ring, to a less strained secondary ion. So that's why this rearrangement happens the way it does, because we got rid of that strained 5-membered ring. The rearrangement provided us with this 6-membered ring, less strain, and we've gone from a secondary ion to a secondary ion. Okay, we're almost done with this mechanism. All we need to do is make this double bond between the 6-membered ring and the fishtail. And we know from our recap of how this mechanism works in general, we have first step is protonation of the OH group to form oxonium. Oxonium leaves, it makes a carbocation. In our case, the carbocation rearranged, and then the last step is departure of H plus to form that new double bond. And so we need the double bond we're going to need the double bond here somewhere. And so we see that, well, what has to happen here is that we have to go through another carbocation rearrangement, right? Because we need the double bond from the 6-membered ring to the fishtail. And so in order to put the positive charge in the right location for that double bond to form, we need another carbocation rearrangement. That's carbon 1. This is carbon 2. Something bonded to carbon 2 pulls out of carbon 2, plugs into carbon 1. The charge moves from carbon 1 to carbon 2. So there's another, this is yet another carbocation rearrangement. And this one makes a lot of sense because we're going from a secondary ion to a tertiary ion. That's downhill in energy. Okay, so that's from less stable to more stable. Okay, now last step is going to be the deprotonation of H plus to put that double bond between the 6-membered ring and the fishtail. And that's our mechanism. Okay, so I see there's some stuff here on the chat. I'm very happy to answer questions on the chat, but I can't interrupt the thread of the lecture to answer a whole lot of questions on the chat, okay? Why can't the double bond be in the ring? Because if I put the double bond here, that's going to be a tri-substituted alkene. This is tetra-substituted alkene, and so we know that the more highly substituted alkenes are the more stable ones. Okay, so how about let's try another one. Let's try another carbocation mechanism. Another alcohol dehydration mechanism, practice in drawing these mechanisms. Okay, so our starting material is this. Add acid. The product looks like it would be this, plus water. Okay, so let's write a mechanism. So we know that a carbocation rearrangement is involved because what has happened is the reorganization of the carbon skeleton. We've gone from a 6-membered ring fused to a 4-membered ring to 2 5-membered rings sharing a side. Now this 4-membered ring has a whole lot of strain, right? So it's clear what's going to happen is that an unstrained 6-membered ring is going to shut down to a 5-membered ring. That's an increase of strain, but we also see that this 4-membered ring, very strained, is going to blow up into a 5-membered ring. So on balance, the total energy of the molecule must be going down, even though we have a less strained system, the 6-membered ring shutting down to a 5-membered ring, and that's bad. But the energy payback of a 4-membered ring blowing up into a 5-membered ring, that's a lot. That's about 100 kilojoules per mole. That's a lot. Whereas a 6-membered ring shutting down to a 5-membered ring, that's only about 7 or 8 kilojoules of strain energy. Okay, first step is totally stereotypical, right? Protonate the oxygen atom, protonate the alcoholic oxygen, and then kick off water So those are the, carbocation rearrangement or not. This is just what always happens in these dehydration mechanisms. And we've got a carbocation down there. Okay, and so now the fun part. We have to figure out what migrated, right? Our goal is to blow up a 4-membered ring into a 5-membered ring and to shut down a 6-membered ring to a 5-membered ring. Okay, and how do we do that? Is that the carbocationic carbon, that's carbon 1. The neighboring carbon is carbon 2. Something bonded to carbon 2 is going to pull out of carbon 2. It's going to plug into carbon 1, and the charge is going to move in the opposite direction. Okay, so now you look at this for a while and you tell me in the chat what migrated. What migrates? Right, just write me a sentence. Tell me what is going to migrate. Migration of methyl isn't going to blow a 6-membered ring down into a 5-membered ring, and migration of methyl isn't going to blow a 4-membered ring into a 5-membered ring. So let's try again. Bottom left corner of 4-membered ring. Yeah, that's exactly what migrates. It's going to be this guy here. We're going to put a big dot on him, right? That's carbon 1. There's carbon 2. Something bonded to carbon 2 pulls out of carbon 2. It plugs into carbon 1, and that is what is going to give us our 2 fused 5-membered rings on an edge. All right, so let's see, try to draw this, preserving the original structure. There's the dot. He migrated. He's now plugged into carbon 1. He's no longer bonded to carbon 2. Carbon 2 is up here somewhere, just trying to redraw this thing in a way that preserves the original architecture of my drawing. And the charge moved from carbon 1 to carbon 2. Okay, and so that's kind of an ugly drawing. So maybe let's fix it. It's a 1, 2, 3, 4, 5, 5-membered ring sharing a side with another 1, 2, 3, 4, 5-membered ring. So this thing could be written like that, with a methyl group here at the ring juncture and a methyl group up here and a positive charge there. Okay, now what? Is it time to form the double bond now? Oh no, it's another carbocation rearrangement, because look where we need the double bond. We can't kick off hydrogen now, because a proton now, because that's going to put the double bond in the wrong place. Tell me in the chat. It's another carbocation rearrangement. What migrated? Oh, it's going to be the methyl group on the left is going to migrate now, because I need these two. It kind of looks like an antenna, like 2 antennas on a little bug or something like that. Yeah, so that's what migrated. We're going from a tertiary ion to another tertiary ion. So we have this migration of methyl. Now we can draw the double bond where we need it, which is here. There's a proton there, a base comes along, it removes that proton, the reaction is catalyzed by acid. And so there's our mechanism that involved these two carbocation rearrangements. Yes? So hope you've heard of a carbocation rearrangement. Okay, so let's stick with this and let's do some more. But now there will be a wrinkle. Now there's going to be a wrinkle. Let's talk about a special kind of a special kind of alcohol dehydration that involves a carbocation rearrangement. And this is called the pinnacle. The pinnacle rearrangement. It's just another flavor of alcohol dehydration. Okay, and so a pinnacle, this is the same as saying pinnacle. This is just the common name for a 1,2 diol. In other words, you have an OH group at one carbon, and on the neighboring carbon, you have another OH group. So a pinnacle is a 1,2 diol, or it's also called a vicinal diol. All right, and so let's see, something like this. Okay, that's a pinnacle. It's a 1,2 diol. So let me ask you in the chat here, anybody have any idea of how a compound like this could be made? Maybe it's something you saw in Orgo 1. How would you synthesize, how would you create a 1,2 diol? How would you create a pinnacle in the laboratory? Maybe it's a reaction you studied in Orgo 1. How do you put in OH groups, side by side OH groups? Well, ozone has the right first letter, so I guess you're close. It would be osmolation with that osmium tetroxide, a reaction of an alkene. So here we would start with an alkene and react that with osmium tetroxide, and then follow that up with workup with sodium hydrogen sulfate. And so that's a laboratory, that's a practical way of making a pinnacle. It may be a reaction that you studied in Orgo 1. Anyway, these guys also undergo dehydration, but those side-by-side OH groups are now going to make the picture a little bit more complicated than what we had before. Once again, acid, heat. The product here is going to be a ketone plus water. See how this pinnacle rearrangement is different from the pinnacle rearrangement is an alcohol dehydration, but you see how it's different from the alcohol dehydrations that we have covered up to now. The alcohol dehydrations we've covered up to now, the product has been an alkene. Here, the product is going to be a carbonyl compound. It could be either an aldehyde or a ketone. In this case, it's a ketone. So you still make a double bond, but this is now going to be a carbon-oxygen double bond rather than a carbon-carbon double bond. All right, so let's go through the mechanism. All right, so we have our pinnacle. Got to get used to writing nice and big. And first step, is going to be protonation of the OH group. Now, in this case, it doesn't matter which OH gets protonated in the first step. The molecule is symmetrical. Anything that the OH group on the left can do, the OH group on the right can do as well. So there are cases, and we're going to talk about one in a second, there are cases in which it does matter which OH group gets the proton in the first step. Here it doesn't matter because the molecule is symmetrical. The OH groups are equivalent to each other. So just for looks, I'm going to protonate the OH group here on the right. I think it's just going to give me a prettier picture. Okay, so there formed the oxonium ion. All right, ho-hum, everything's the same as before. And now what's the next thing that you think is going to happen? Yep, departure of oxonium to make a molecule of water. So it's just the same first two steps that we've encountered before, minus H2O. And so we have this carbocation here. He's secondary, and now it's time for the rearrangement. This is carbon 1. Carbon 2 is next door. Something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1. The charge is going to move from carbon 1 to carbon 2. So it's just the same, the same ideas that we've been talking about in all of the pinnacle in all of the dehydration mechanisms up to now. Okay, and now what could, so this is carbon 1. This is carbon 1, this is carbon 2. Something bonded to carbon 2 is going to pull out of carbon 2, and what that thing is going to be is one of these methyl groups, right? It's not going to be this OH group, and I'll tell you why in a second. So it's going to be one of these methyl groups is going to pull out of carbon 2 and plug into carbon 1, and what we get is this carbocation. And here we have achieved a resonance stabilized carbocation. This oxygen atom has an unshared pair of electrons that it can kick in to that carbocation to make a resonance stabilized carbocation. So this is why OH doesn't migrate in the pinnacle rearrangement, because we want to achieve this resonance stabilized carbocation. If we moved OH, we wouldn't get a resonance stabilized ion. Okay, and so now that looks very much like our product, right? If we look at our product that we're trying to come up with, it's a methyl ketone on one side and a chicken foot on the other side. It's a methyl ketone and a chicken foot on the other side. And so the last step is the deprotonation of the carbonyl group, and there's our final product, which is this ketone. All right, so that's the pinnacle rearrangement. It's just another dehydration of an alcohol that goes through a carbocation that rearranges, but the starting material is slightly different. Okay, so let's do another one. All right, so how about something like this? H plus heat. So I think maybe you would be ready to predict the product, and then we're going to write a mechanism. So why don't you see what the product is? Is it a pinnacle? Oh yeah, it's a 1,2 diol. What would be the structure of the product? Whenever we talk about these reactions, one of the skills you want to be in control of is to be able to predict what's going to happen. What's the product? Okay, about to divulge the answer here. The product will be a ketone like this, spirofused. That means sharing one carbon with a 5-membered ring like that. And then the inorganic product of the reaction is water. Did you get that? Yeah, don't answer that. Okay, so now let's write out the mechanism. Okay, so once again, the pinnacle is symmetrical. It doesn't matter which OH group gets the proton at the beginning, because the molecule is symmetrical. So first step is going to be protonation of an OH group. I'm going to protonate that one. And I get this guy, oxonium, right? And then oxonium leaves minus H2O. There's the carbocation, right? There's the carbocation. And now we would like to do the rearrangement. So this is carbon 1. There's carbon 2. We want to bring, in the pinnacle rearrangement, we want to bring that positive charge underneath the surviving OH oxygen. That way we can make a resonance stabilized carbocation. So that's carbon 1, that's carbon 2. We have a bunch of carbon 2s over here, but none of those are going to bring the positive charge to underneath that OH oxygen. So there's carbon 1, there's carbon 2. Something pulled out of carbon 2, the dot, migrated over to carbon 1, and the charge moved from 1 to 2. Okay, so this is going to be ugly. There's the 5-membered ring. There's the dot that migrated. The whole point of that migration was to bring the dot, was to bring the positive charge there. Okay, just trying to redraw that in a way that preserves the original structure of the rearranging carbocation. Okay, so now this is going to be the same as, it's a 6-membered ring from the dot, 1, 2, 3, 4, 5, 6, and back again. Yep, 6-membered ring. OH down here, positive charge there. 5-membered ring sharing one carbon like that. Right, and this is that resonance stabilized carbocation. Last step is going to be the deprotonation. We could write a resonance form, but I won't, not necessary. Last step is the deprotonation of that oxygen atom, and there's mechanism for the formation of our final product. So how'd that go? Well, I hope. Okay, so now let's look at the next level of complication where our starting pinnacle is not symmetrical, and now we have to decide which OH group gets it in the first step. pH, that means a benzene ring. H plus, heat. Is it a pinnacle? Is it a 1,2 diol? Well, it most certainly is. First step is going to be protonation of one of those OH groups, but now this thing isn't symmetrical anymore. So tell me in the chat, which OH group is going to get it? The OH group on the left or the OH group on the right? Which OH group is going to get a proton? And before you rush to judgment, remember what happens. Protonation of the OH group, then oxonium leaves to make a carbocation. That is the basis for your decision making here. So which OH group gets it? The guy on the left or the guy on the right? Oh, it's going to be the OH group on the left. Oh, jeez. Oh, this crap. What's up?
Are you teaching?
Until 1:30.
Okay. Yeah, they screwed up my room again.
What else is new? So it's going to be the OH group on the left gets the proton. So we have oxonium, right? And then after the protonation step, what happens is departure of water. And so what, all right, so now I told you which OH got protonated, and now you tell me in the chat why. Why did the guy on the left get it? Closer to pH, and so what does that mean? Yeah, that positive charge is stabilized by resonance with the benzene ring. pH means benzene, right? Maybe yes, maybe no, you've seen that before. So that carbocation is stabilized by resonance with the benzene ring. Now, if I had protonated the OH group on the right, if I protonated this guy, that would have formed oxonium. That would have left as a molecule of water. I would have gotten a terrible, highly strained tertiary carbocation that isn't taking advantage of resonance. And remember, the carbocation is sp2 hybridized, and that means 120-degree bond angle. If I put a carbocation into a square, that's horrendously strained. So the reason that the OH on the left got the proton, the reason it left as water is because I have a resonance stabilized carbocation. So this is when the pinnacle is not symmetrical. This is how you're deciding which OH group gets the proton in the first step. It's going to be the proton that can furnish the most stable carbocation. Okay, so now it's time for the rearrangement. We need to bring this positive charge underneath this surviving oxygen. That's carbon 1, that's carbon 2. Something bonded to carbon 2 is going to pull out of carbon 2. It's going to plug into carbon 1. There's carbon 2. What all is bonded to carbon 2? It's going to be this dot or this guy down here, but it's symmetrical. Kind of hard to see that, but it's symmetrical, so it doesn't matter whether the carbon up here at 12 o'clock migrates or the carbon down here at 6 o'clock migrates. All right, and so there's our migration. And now trying to draw this in a way, hoping to make this more understandable in a way that maybe preserves the original structure. There's the dot. He's now plugged into carbon 1. The charge has moved from carbon 1 to carbon 2. It's a 1, 2, 3, 4, 5-membered ring, resonance stabilized. That's an equal sign. This is a 5-membered ring. Put OH down here, put the positive charge there, put phenyl over here. So it just redrew that, Okay, and now the last step, let's do it this way. Last step is deprotonation of that carbocation, and so that would be our product. Okay, going to move on to a new family of reactions now. Is there any questions about this before we move on to something new? Is there a trick in finding the dotted carbon after it has rearranged? Well, not really. There's nothing tricky about it. Here's the trick. Positive CH2, CH2 dot. It's just tracing where the, just look at the two structures and you can figure out where the migrating carbon went. Okay, so let's see. Let's take a little break now. Look at some pretty pictures. So a dehydration, for those of you who, for the lucky ones out there, the lucky ones who will one day take biochemistry, you'll see that these dehydrations are all over biochemistry, these dehydrations of an alcohol. Maybe you've heard of the citric acid cycle, also called the Krebs cycle, also called the tricarboxylic acid cycle. This is one of the three main energy producing pathways in a physiological system. The other two being glycolysis, that's the breakdown of sugar, and oxidative phosphorylation. Those are the reactions that involve ATP. Maybe you've heard of that. Okay, so in the citric acid cycle, we have this dehydration of this guy here. This is called, this is citric acid, and it reacts with the enzyme aconitase, and we get this dehydration of alpha, that we get a new double bond between alpha and beta, and this is called cis-aconitic acid. This is one of the steps of the citric acid cycle. In the laboratory, we would use sulfuric acid and boil the hell out of it. Well, obviously, that's not an option in a physiological system. So instead of acid and heat, the catalyst in a physiological system is an enzyme. And in this case, it's this enzyme aconitase. And so this is a ribbon drawing of that enzyme. The lucky ones among you will be seeing a lot of these in biochemistry. Those red tubes represent regions of the beta pleated sheet. It's just like a corrugated segment of that enzyme. And the alpha helix, the red tubes, I guess here are the helical regions, and the blue arrows, those are regions of the pleated sheet. And this reaction, here's another one, another dehydration in the citric acid cycle, where L-malic acid is dehydrated to fumaric acid. Again, you get a new double bond between alpha and beta. This is another step of the citric acid cycle that has two dehydrations in it. This is fumarase, the enzyme that catalyzes that second dehydration, molecular weight about 55,000. So this is a huge molecule with lots and lots of amino acid residues. And once again, these red corkscrews here, these are the regions of the alpha helix. And the yellow arrows, aren't too many here, that's the beta pleated sheet. So what does this remind you of? Yep, an 80s, 1980s style high hair. And the deficiency of this enzyme, fumarase, deficiency of this enzyme leads to retardation, brain malformation, and seizures. I don't know if any of you have a whole lot of experience with young babies, but maybe in this image you can see this huge bump here on this baby's head. That's not supposed to be there. That is a swelling that is caused by water being trapped in the brain. This baby doesn't have that fumarase, so that dehydration of malic acid to fumaric acid can't happen, and that is very bad news. What do I want to do now? Okay. So now let's talk about a new family of reactions involving the alcohol. Okay, so let me ask you in the chat to complete the following sentence. The OH group is a very bad fill in the blank. The OH group is a very bad leaving group. Exactly. The OH group is a very bad leaving group. But you know what? There are, we just saw a reaction in which the OH group functions as a leaving group. That's what dehydration of an alcohol is all about, the OH group functioning as a leaving group. But in that mechanism, OH doesn't leave. It's actually water. It's actually the oxonium that leaves. The OH can't leave until it undergoes protonation, and then it departs as a molecule of water. But OH itself will not take off. But there are bazillions of ways of making an alcohol. But in many ways, that OH group represents a chemical dead end because you can't make it go away. You can't transform it into something else. So what we're going to talk about now are a bunch of reactions that accomplish just that. They convert the OH group into a good leaving group so that we can do additional chemistry. All right, first up, Darzens. This is named for, I think he was a French guy, Darzens reaction, or let's call it, Darzens halogenation. So this Darzens halogenation, he was a French chemist, I believe, and came up with this reaction in the closing years of the 1800s. It's been around for a while, but it's still pretty useful. Okay, and the overall reaction here is going to be the conversion of an alcohol. This must be primary or secondary, and it can never be tertiary. It has to be a primary or secondary alcohol. This reacts with thionyl chloride, SOCl2, and we also need pyridine. Okay, so pyridine, this takes an awful long time to say, an awful long time to write. So this thing is just abbreviated PYR. So if you see PYR, that's what that means. So it's a primary or secondary alcohol plus thionyl chloride plus pyridine. The product, we convert that primary alcohol, primary or secondary alcohol, to a primary or secondary chloride. And chloride is a pretty good leaving group, right? Now we can do stuff with when the Cl is on there. The other products of this reaction will be SO2 plus Cl minus plus the conjugate acid of pyridine, which is called pyridinium. And so that takes an awful long time to say, awful long time to write. So this is just conventionally abbreviated HPYR plus. Okay, so the overall reaction is the conversion of an alcohol, which has a bad leaving group on there, to a chloride, which has a good leaving group on it. And we'll see in the mechanism, we'll go through this mechanism in a second, and we'll see that this is this happened with inversion of configuration. Okay, so Darzens halogenation. It's a way of converting the OH group to a chloride. And then we'll talk about, after we talk about the mechanism, then we'll spend a few minutes, a few seconds talking about why anyone would care about Darzens halogenation. All right, so let's write out the mechanism. But before we do that, maybe in a previous orgo class, you've heard of the words nucleophile, nucleophile, and electrophile. What's a nucleophile? A nucleophile is something that is electron rich, right? And that E with that negative charge superscripted, that's just my symbol for an electron. A nucleophile is something that's electron rich. The counter image of the nucleophile is the electrophile. And what's an electrophile? It's something that's electron poor. So most of chemistry is nucleophiles chasing around electrophiles. So it's something that has a lot of electrons chasing after something that doesn't have as many electrons. Okay, so maybe you are acquainted with those terms from a previous course. They're going to come in handy this term. Okay. So the mechanism here is, let's see, let's start with an alcohol. And I guess I want to make this alcohol, a chirality center, because one of the important features of this reaction is its inversion of configuration. So maybe something like this. Wedge OH dash dash dash. Okay, I didn't make it a chirality center, but that's good enough. All right, so is this a candidate for Darzens? It is. It's a secondary alcohol. The alcohol has to be primary or secondary. This is a secondary alcohol. Okay, now this thing reacts with thionyl chloride, that SOCl2 stuff. And the Lewis structure of SOCl2 is that. Okay, so now tell me in the chat, who is the nucleophile here and who is the electrophile? The electrophile is easier to spot. So tell me, who is the electrophile in this reaction? Most of these reactions involve nucleophiles, that's stuff that's electron rich, and electrophiles, that's stuff that is electron poor. So look at these two guys and tell me who is the electrophile. Okay, the electrophile is SOCl2, but I need something a little bit more to the point than that. Yep, the SOCl2 has the electrophile, but what is the actual electrophile? Oh, the actual electrophile is going to be the sulfur atom. Sure, because this sulfur atom, this poor little sulfur atom, is bonded to all of this highly electronegative oxygen and chlorine. It is having its electrons sucked away from it by the highly electronegative oxygen and those two highly electronegative chlorines. So the sulfur atom in SOCl2, the sulfur atom in thionyl chloride, that is the electrophile. The electrophile is going to be attacked by a nucleophile. Tell me in the chat, who is the nucleophile? Who is the nucleophilic atom? Yes, the oxygen of the OH group. That is the electron-rich atom indeed. Okay, so the first step of this reaction mechanism is going to be the attack of the nucleophile on the electrophile. That electron-rich oxygen attacks the sulfur. Okay, and so the double bond reorganizes itself this way. All right, so just so that I come up, I have to write very big here, and I'm not used to that, and I want to come up with a pretty drawing. So I'm just going to try to switch this a little bit. So this was my wedge. Here's my 6-membered ring. There's my dash. So that attacks sulfur, O minus, Cl, Cl. Okay, so that's what we get when the nucleophile attacks the electrophile. Okay, a couple of comments about the structure that I've drawn is that these arrows represent the motion of electrons, not the motion of atoms, right? This arrow is saying that the electrons around this oxygen attacked the sulfur atom. All right, and since this oxygen is neutral, and since this arrow represents the pushing away of electrons from something that's neutral, that oxygen atom pops out positive. So this has to make sense to you, right? Without these formal charges, the structure is just wrong, right? You can't omit this formal charge here. And what has to make sense here is that these arrows represent the motion of negatively charged electrons. When you push negatively charged electrons away from something that is neutral, that neutral thing is going to pop out positive. Okay, this arrow here represents the motion of electrons. So this arrow here on this sulfur oxygen double bond, that oxygen at 12 o'clock is neutral, but that arrow shows I'm pushing electrons toward it, it pops out negative, right? So that's why I put that negative charge there on that oxygen atom. Okay, so that's the first step, is that nucleophile, the electron-rich thing, attacked the electrophile, the electron-poor thing. And notice I was able to identify what was and what was not a nucleophile and an electrophile on an atomic basis. Okay, now it's time for the pyridine to get involved. The pyridine, this is a base. It functions as a base, right? And remember, we call this thing PYR. This functions as a base. It's going to come in here and remove this proton from this oxygen atom, and then oxygen is going to gobble up that electron pair. And the reason this happens is that oxygen is highly electronegative. It doesn't want to be positively charged. It wants to gobble up electrons and to be neutral or negative. Okay, so the pyridine comes in and removes that proton, and the product of this reaction is that HPYR plus stuff, right? I'm not going to rewrite the structure because it's going to get too crowded. All right, and so now I have dash, 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 wedge, O, oxygen up here, Cl, Cl. And again, the charges have to make sense to you, right? This oxygen was positive. This arrow shows I'm bringing negatively charged electrons to something that is positive. When I bring negative charge to something that's positive, it pops out neutral. Okay, and so now, next thing is that electron pair on this sulfur comes down here. It's going to remake that sulfur oxygen double bond and complete the following sentence. Cl is a very good what? Leaving group. So Cl is a very good leaving group. So what happens now is that departure of one of these Cl's from the sulfur atom. So now I have Cl minus, right? And the charge makes sense. the chlorine is neutral. That arrow shows I'm bringing electrons toward it. So the so the sulfur atom is now that chlorine atom is neutral. And what I've created here is a chlorosulfite ester. That's not, it's not really matter what it's called, but this group here, this chlorosulfite ester, just give me a second. This thing here, chlorosulfite ester, this is a very good leaving group, right? It's not probably not one of the leaving groups that you covered in any Orgo 1 class, but it is a very, very good leaving group. And what has happened is that this very good chlorosulfite leaving group has been created in the company of Cl-, which is a decent nucleophile, right? This guy is electron rich. This carbon is sp3 hybridized. It has a good leaving group on it. So what happens is the Cl attacks the carbon that bears that chlorosulfite group. This is an SN2 reaction. And so that explains why the carbon atom, why the alcoholic carbon atom, why this guy has to be primary or secondary, because we never see a SN2 reaction on a tertiary carbon. So the Cl comes in as the nucleophile. This bond breaks like so. And then this bond breaks like so. So another thing we know about SN2, other than we never see an SN2 reaction on a tertiary substrate, another thing we know about SN2 is that it happens with backside attack. In other words, the leaving group is in the front of the molecule, the nucleophile comes in from the back. The leaving group is in the back of the molecule, the nucleophile comes in from the front. The leaving group is on the top of the molecule, the nucleophile is going to come in from the bottom, right? So we're ready to draw the next intermediate here. So we'll just put this here on the side. Put this here on the side, and we'll get our piece of paper here. And so the product is going to be the chlorosulfite leaving group was on a wedge. Cl kicked it out in an SN2 reaction, so the Cl is now on a dash. The inorganic junk we don't care about is sulfur dioxide and more chloride. Okay, so there's our Darzens halogenation mechanism. And now, and so notice that we had this inversion of configuration, that dash, that wedge OH became dash Cl. That's a feature. Now, the reason of this reaction, and we also see that one of the reasons that this chlorosulfite leaving group is such a tremendous leaving group is because we get this SO2, this comes off as a gas. So do you guys remember delta G is equal to delta H minus T delta S from Gen Chem? So the entropy of this reaction is tremendously positive. So that's extremely favorable. You're creating a gas, the delta S is going way up. And so that's one of the reasons why this chlorosulfite leaving group is so good. All right, so now why would anyone care about Darzens halogenation? Is because now we've put a good leaving group, Cl, on a molecule. We've converted the alcohol to something that has a good leaving group, and now we can do all kinds of chemistry with that Cl group, principally SN1 and SN2 type of chemistry. So, okay, so that's Darzens halogenation. I think I have a pretty picture to show you, maybe, hope so, about Darzens halogenation. Yeah, here it is. Benadryl. Heard of Benadryl? Maybe you've taken Benadryl. And so the first step in the synthesis of Benadryl is you start out with this alcohol. This is secondary. Add thionyl chloride and pyridine, and then that puts this good leaving group on it. And now this leaving group is kicked off by a nucleophile. We'll talk about that in a second. So this Darzens halogenation is used in the synthesis of Benadryl, which used to be an anti-allergy medication, but it has too many side effects. Principal side effect being somnolence. It puts you to sleep. Whoa, 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 whoa. Okay, so here's Darzens halogenation in the synthesis of iprindole. This is a tricyclic antidepressant. And so once again, here's that primary alcohol, react that with thionyl chloride. It replaces the OH group with Cl, and then there's more chemistry leading to the final production of this antidepressant. Speaker view. All right, so that's very nice, that Darzens halogenation, but it's not the only reaction that we can use to convert the OH group, which is a bad leaving group, which is a terrible leaving group, to a good leaving group. So that's our next little candidate, that's our next little reaction here, which is now sulfonation. Sulfonation of an alcohol. Okay, here the overall reaction will be, you take an alcohol, and now this alcohol can be either primary or secondary or tertiary, but yeah, it's all right. Can be primary, secondary, or tertiary, so it's not really restricted to any kind of alcohol, really. And this stuff reacts with what is called a sulfonyl chloride. Okay, so that's the sulfonyl chloride. It has a sulfur atom double bonded to two oxygens, single bonded to a chlorine, and also bonded to something called, which I'm just calling Z now. I'll talk about that in a second. Z can be a couple of different things. I'll talk about what they are in a second. The reaction, once again, uses pyridine, right? PYR. And the product here is going to be the product of sulfonation which is that. And then we have some inorganic and organic junk that we don't care about. We'll see that when we talk about the mechanism in a second. And now this guy here, he's a very good leaving group, right? This is called a sulfonate. This is not a leaving group maybe that you saw in any Orgo 1 class. This would be a new leaving group for you or for most of us. So that's a very good leaving group. So once again, this is a way of converting the OH group, which is a terrible leaving group, to something that's a good leaving group. Okay, now what about this Z business? Okay, so Z can be a lot of things, but there are some standard entities, standard moieties that Z can be. So let's make a listing of those. Z can be a benzene ring with a methyl group on it. And when Z is this is called a tosylate. And the starting compound here would be called ClTs, where this TS represents the sulfur atom double bonded to those oxygens, and where Z is this. All right, so something like this, let's say. Right, that's called tosyl chloride. But this whole thing here, I guess I better circle it. This whole thing here, that is abbreviated TS. So you see TSCl. TS is not an element on the periodic table. TS means tosylate. It means this that this is the sulfonyl chloride that was used. All right, so I'm going to return to this in a second. Maybe try a different tactic here. CLS can be shoot. Right, and this is called TSCl, tosylate. Can also be just put a methyl group here. This is called mesylate. And so this is another tremendous, this is going to be another tremendous leaving group. It's called mesylate, and its standard abbreviation is MSCl. And that MS means, you know, this whole thing here, that is TS. And this whole thing here, that is MS. Another very popular sulfonating agent is one in which that Z group is trifluoromethyl, and this is called triflate. And its standard abbreviation is TF. So this is that, right? And there are just dozens and dozens and dozens of these sulfonating agents. These are the three most common ones. And this is what I would like for you to be able to recognize. Okay, so those are the sulfonating agents. So now let's talk about the mechanism of sulfonation. All right, so once again, we'll go with that same alcohol that we went with before, but now I know I better write it this way to start out with so I don't have to do any kind of drawing gymnastics on it. So we know that OH, that's the nucleophile. That oxygen atom is the nucleophile. And so now that is going to react with the sulfonating agent, right? And I'm just going to put Z here, right? And I just went through a bunch of stuff that Z can be, so let's just leave it at that for now. And so this oxygen atom, that's the nucleophile. The sulfur atom, that's the electrophile. And so the sulfur atom is an electrophile because it's bonded to all of that highly electronegative oxygen and sulfur. And so the nucleophile attacks the electrophile. So we get an intermediate that is going to look like, so you better shove these up here. Remember back in Gen Chem, did you study Vesper? Maybe you remember the trigonal bipyramidal shape, right? Does any of that ring a bell? The steric number of 5, the trigonal bipyramidal shape when you studied Vesper? Well, that's what's going on with this sulfur atom here. Okay, and so now, so this is very similar to the first step of Darzens. And now these electrons, whoops. Now the pyridine gets involved. PYR in, HPYR plus out. What happened is the deprotonation of that oxonium. So we already went through all of that. So it's just comparable. And now these electrons come down, and Cl is a good leaving group. So these steps of the sulfonation mechanism, very similar to Darzens halogenation, except that the starting material is different. And so now we have Cl minus rolling around in the reaction mixture. And our product is this all right, and we've converted the OH group to a very good leaving group. Okay, so now in Darzens halogenation, what we saw is that this Cl was going to wheel around here and kick out this good leaving group, but that's not what happens. That's not what happens here, because what's going to happen here, I'm going to write this in a little box here, is that this Cl minus would much rather do an ionic reaction with the HPYR plus than to function as a nucleophile in this case. So we have HPYR plus gets together with Cl minus to form PYR dot HCl. Right, so we do get the Cl in the reaction mixture, but it ordinarily, this sometimes can be a problem in the laboratory, but ordinarily the reaction stops here. Okay, compare and contrast. So a lot of the steps of this mechanism for sulfonation were similar to the steps in the Darzens, but what jumps out right away is that although both of these reactions are ways of converting the OH group to a good leaving group, the thing that pops out right away is that the Darzens halogenation happened with inversion. Wedge OH became dash Cl. But for sulfonation, wedge OH stayed wedge OTS or wedge OMS or wedge OTF. So that Darzens halogenation happens with inversion, whereas sulfonation happens with retention of configuration. And that's great for us in the chemistry laboratory because now we have control of stereochemistry. Okay, so let's do some problems where we're looking at that complex reactions. All right, so let's go back to this alcohol here, wedge OH, dash, dash, dash. And over here, SOCl2 and pyridine. Over here, tosyl chloride and pyridine. Okay, now real quick, write the structure of the products of both of these limbs, right? I'm not going to ask you in the chat, but this is what when you're studying organic chemistry, this is one of the things that you're studying, being able to draw the structure of the product, right? Who lives there and who lives there? Okay, this SOCl2 converts the OH to Cl, but it does so with inversion. Wedge becomes dash or dash becomes wedge because it's an SN2 reaction. So do you guys remember the cis trans? Do you guys remember or ever heard of the cis trans nomenclature? You see how this methyl group and this OH, they're trans. Now they're cis. Okay, what happened over here? Tosyl chloride and pyridine. This converts the OH group to a sulfonate, but it does so with retention of configuration. Wedge stays wedge and dash stays dash. OTS. Right, and notice how this was trans and it's still trans. Okay, and the reason I'm belaboring this point is that these two reactions are complementary. They give us control of stereochemistry. So now what is usually done next is now since that's a good leaving group and that's a good leaving group, now we want to kick it off with a nucleophile in another SN2 reaction. So we could react this with cyanide. We could react this with cyanide. We could react this with cyanide. This is an SN2 reaction. This is an SN2 reaction. And what do we know about SN2? Inversion of configuration, backside attack. So that here, the final product is going to be dash, dash, dash methyl, but the new CN came in on a wedge because the Cl, the leaving group, was in the back and the nucleophile came in on a wedge from the front. And so notice this is trans. What happened over here? Well, this is another SN2 reaction. Wedge, 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 pre-existing methyl group. The leaving group is on a wedge. The nucleophile is going to come in on a dash. So this is cis. Okay, let's see. What is someone asking me here? Why is adding, well, let me ask you. Let me ask you, have you ever studied SN2? Right, this is a private chat. This is just between me and you. No one can see what you're saying. Ever studied SN2? Yeah, well, the SN2 nucleophile is typically an anion, right? Is water an SN2 nucleophile? It is not. So in the SN2 reaction, the nucleophile, the thing that kicks out the leaving group, is usually anionic, negatively charged. So that's how I know it's SN2, because cyanide ion is a typical SN2 type of nucleophile because it's ionic, anionic. Water is not SN2. Alcohol is not SN2. Acetic acid is not SN2. All of those are neutral, but the negative versions of all of those would be SN2. That's how I know it's SN2. The reason I ask you is because, you know, everybody, lots of people are coming in here from all kinds of different Orgo 1s, so I have no idea what you covered in Orgo 1. This is great for us because this is great for us organic chemists because now we know if we want the dash CN, we know how to get it from the wedge. If we want the wedge CN, we know how to get it from the wedge. If we want the wedge from the dash, we would know how to get that and so on and so forth. Okay, so let's try some more problems. So how about something simple? Okay, so that's what I want to do in the laboratory. Write out the steps. What do I do? I'm asking you to write out a recipe. Okay, let me check out the chat here because I want to see who is coming up with something good. Is that a double bond? Oh, that's not good. Is that a double bond O connecting to the ring? This guy here? This guy here? This guy here? Yeah, the only double bond here is this carbon-oxygen double bond. Everything else is supposed to be a wedge. Right, this is a wedge. I don't know if I'm answering your question. That's a wedge, and that's a wedge. The only double bond is here. Okay, now you write out the recipe. What's the first step? Okay, I'm waiting for the recipe. I'm waiting for the right recipe. Do what, then do what, then do what? What's the recipe? Anybody want to give it a shot? Oh dear. Not too good. Dash became wedge. See that? See how dash became wedge? Okay, look at what we just talked about. Look what we just talked about. Wedge stayed wedge. So SOCl2 is not the right way. That's not the recipe. Wedge stayed wedge using SOCl2. It's not what we want here. We want to switch the stereochemistry. This is the right recipe. Tosylation and then SN2. So the recipe here would be, first step, maybe something like tosyl chloride and pyridine. Wedge, OTS, right? Dash stays dash with this in this tosylation, because when you look at the tosylation mechanism, the carbon that bears the OH group never got involved. I don't see this carbon right here? I don't see it getting involved in any of these steps. It did nothing. All of the action was with the oxygen atom. Okay, now I want to kick this wedge off. I want to put on this nucleophile by kicking this OTS group off. And so that's going to be another SN2 reaction. And I'm going to use acetate. It's going to be an SN2 reaction using acetate as the nucleophile. And so that's going to, the leaving group is in the back. It's going to come in, the nucleophile is going to come in from the front. Yes? Okay, let's try another one. How about a hard one now? How about something really hard? Those of you who were with me last semester, you know I love this thing. I'll call this the witch's hat molecule. Okay, give me the recipe now. So what am I doing here? what's going to be the first step? Is that going to be tosylation again? See, exo, that's what we call this position here. It doesn't matter what it's called. Exo stays exo. Wedge stays wedge using that Darzens halogenation. Yeah, so I don't want to have tosylation here. I want that Darzens halogenation because after the second SN2 reaction, the exo position returns to being exo. SOCl2, pyridine, Cl is down like that now. And what's the nucleophile here? What am I adding here in the second step? Tell me in the chat. What am I writing above and below the arrow here now? I'm writing I minus, right? Not plain old I, not I2, I minus. But you know, we can't buy a bottle of I minus because because every negative charge has to be satisfied by a positive charge. So to make it even more realistic, I'm going to use Ki, potassium iodide, or I could use sodium iodide, right? But the important thing here is the I minus. Okay, one more reaction in which the OH group is converted to a good leaving group. And that is called the Mitsunobu reaction. You know, the greatest honor, I guess, or one of the greatest honors that can be bestowed on an organic chemist is to have a reaction name for them. And so we have a lot of these so-called name reactions. Darzens halogenation is an example. And this Mitsunobu reaction is another example. This was a Japanese chemist who discovered and developed this reaction in the 1970s. So this is fairly modern, especially when compared to Darzens halogenation, which is over 100 years old. So this is a pretty modern reaction. And it's another way of converting the OH group, which is a bad leaving group, to a good leaving group in order to do SN2 chemistry on it. All right. Mitsunobu reaction. Overall reaction. Okay, so this has inversion in it, just like Darzens halogenation. So I'm going to write something that looks like this. Hope this isn't too confusing. R prime. So those R's can or cannot, or may not be different. I'm putting an OH group there and hydrogen there. So that could be a chirality center. All right, this has to be primary or secondary and never tertiary because an SN2 reaction is involved somewhere down the line. And then there is the protonated form of a nucleophile. I'm just going to call that H-nuc. And what would be some concrete examples? I'll give you that in a second. All right, and then we have triphenylphosphine, PPH3, and then I'm going to have to draw a big, huge arrow here. ET, that means ethyl. This stuff, that's a nitrogen atom. That's another nitrogen atom. This stuff, and this is called diethyl azodicarboxylate. But that takes an awful long time to say, and the structure takes an awful long time to write, so that the acronym for diethyl azodicarboxylate, dead. Blah! Diethyl azodicarboxylate. So anytime you see dead above and below the arrow, you know you're with the Mitsunobu. You're in the Mitsunobu reaction. Okay, and the products are going to be the nucleophile ends up where the alcohol used to be, but note the inversion of stereochemistry. The OH was initially in the front, the nucleophile is going to come in the back. The organic junk we don't care about. This is what we care about, this guy here, what the alcohol turned into. The organic junk we don't care about are triphenylphosphine oxide, that just gets dumped in the garbage, and this diethyl azodicarboxylate, which is this very same thing we started with. And this is abbreviated H2DEAD. Okay, so that's the Mitsunobu reaction. And let's compare and contrast to what we've been talking about before. Darzens and sulfonation, that was a two-step thing, right? First step, convert the alcohol to something that has a good leaving group on it. Second step, knock that good leaving group off with a nucleophile. This Mitsunobu is a one-step reaction where all of that is going to happen all in one pot. It's not one step, but you don't need two separate steps. The nucleophile that you want to replace the OH group is in there from the beginning. Okay, so let's look at what H-nuc can be and what it cannot be. H-nuc must have a pKa less than 12. So what can H-nuc be? H-nuc can be a carboxylic acid. What else can H-nuc be? H-nuc can be a phenol, pKa 10. What else can H-nuc be? H-nuc can be a thiol, pKa also 10. No good. Anything where the H-nuc isn't acidic enough, water or an alcohol, no good. An amine, no good. Right, so there are limitations to what the nucleophile can and cannot be in a Mitsunobu reaction. All right, so let's try a product prediction and then wind up for the day. So let's go back to our old friend, this guy. PPH3, DEAD, draw the structure of the product. It's a Mitsunobu. How do you know? It's the Mitsunobu recipe. You see that DEAD stuff. You see that dead stuff. And so this is a reaction where the OH group is going to be converted to a good leaving group and the nucleophile is going to come in. It's all going to happen in one step with inversion of stereochemistry. So there's the nucleophile. It's a carboxylic acid. pKa of the carboxylic acid is about 5, so that's good. And so this part here, I'm circling it, that's the nuke in H-nuke. And it happens with inversion. So the product here is going to be dash, 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 O. It's a way of making an ester in one step. We'll talk about the mechanism next time. All right, so